everyone. Welcome to another session of our seminar. And it is a pleasure to introduce you Meera Mainkar from Central Michigan University, who is going to talk about something really interesting. What is the title is there, Preserve One, Preserve All. Thank you very much, Mira, for accepting our invitation. So I give you can start as soon as you want.
Okay, thank you. Thank you so much to the organizers to invite me. And my special thanks to Carla, who couldn't attend because she's, I think, busy this time. Um, and I have kept the work that I'm doing with Carla at the back of my chair that we were collaborating on. So hopefully I will be able to give that talk maybe sometime later in the seminar. But today I'm going to talk about Preserve One, Preserve All. And this is a work that we have done, I have done with Benjamin Schmidt he's in Michigan State University, which is about 70 miles away from our university. And some time ago, actually, we have worked with this, and we are still kind of in the process. So the work is already on archive, but it has not published yet. So, okay. So what I'm going to start today, and I hope that this method works, like writing on the iPad, because it slows me down, and that's why I chose this. The setup is the following. So just hold on, setup. So you start with a metric space. So suppose you have a metric space xt, and you have a function from x to x, just a function. Then I want to recall certain definitions. Number one is that we say f is an isometry if the distance between the image points is the same as distance between the 2 points in X. And F is surjective. Okay. Now I want to define a few more things. So for that, I need the following set for R positive. Positive real number, and I want to define a set of points like the order pair A, B in X with distance R, that specified distance R. And definition 2 is that we say that F preserves distance R if there are 2 points, at least 2 points with distance R. So XR is not empty. And whenever the distance between A and B is R, then the distance between image points is also R. So, and distance between F of A, F of B is equal to R whenever distance between A and B is equal to R. Okay. And number 3 definition is that we say that F preserves all distances if the distance between A, B is the same as distance between f of A, f of B for all A and B in X. So if we see the definition of isometry and compare it with f preserving all distances, it's clear that f is an isometry if f preserves all distances and f is surjective. Just rewording the definition. Okay, let's see some examples, very, very basic examples and non-examples mixed together. So let's see just a function, and we are going to take a function from R to R. Okay, and we are going to define function as follows. So you say f of x is equal to x if x is an integer, and it is x plus 1 if x is not an integer. Let's see what is a PF, or sorry, not PF, but what distances does F preserve? Okay, so let's say I want to claim that the distance 1 is preserved. So let's try to see this really quick. Preserved. So suppose you have 2 points, and the distance is just a Euclidean distance. So suppose you have 2 points with distance 1. Then let's try to see why distance between f of A and f of B also is 1. So we can consider 2 cases, and this is very straightforward. So suppose A is an integer, and then that forces B to be an integer, and so then you have distance between f of A and f of B. It's just going to be 1 because this is A and this is going to be B, right? If A is not an integer, then B is also not an integer, and that implies that the distances are just shifted by 1. So again, the image points will have distance 1 because this is A plus 1 and this is B plus 1. Okay. All right, so there is nothing special about 1. The only thing which is special about 1 is it is just positive integers. So in the same way, one can conclude that all positive integer distances are preserved. So in fact, all integer, and of course positive, we don't say negative distances anyways. So distances are preserved. The same logic. Now the question is whether you have anything else other than integral distances preserved. So question is that any more distances preserved? And answer is no, because for example, if you take, say, 1/2, let's say 1/2 is preserved or not, then you can easily see that this is true, but what is the distance of the image of 0 and distance and the image of 1/2? This is equal to 0 by definition of f, but this is equal to 3/2 because you're going to add 1 because 1/2 is not an integer by definition, and hence this is 3/2, and that is not equal to 1/2. So 1/2 distance is not preserved. In fact, no other distances are preserved. Only integer distances are preserved. So I'm going to define actually a set of all preserved distances. So set of preserved distances, and we are going to denote it by PF. That was I was talking about at the beginning before introducing that. So it has all the distances that are preserved by function f. So first of all, there should be at least 2 points in the space with that distance r, and distance between AB is equal to r should imply that distance between f of A, f of B is also equal to r. So you collect all of those numbers r. And so, for example, in the example that I just showed you, f from r to r, where f fixes all the integer points mapped to the same points, but then non-integer numbers are mapped to that number x plus 1. In that example, we just saw that PF is equal to positive. Okay. Are there any questions?
Yes. So, good morning. Can you hear me?
Yeah.
Okay. Can I see again the definition of F?
Yeah. Here.
Okay. So if it is integer, let it fix, and if okay. Thank you.
Yeah, no problem. Any other questions?
Not so far.
Okay. All right. So now, so this is what is happening like that in function from, and I just gave you one example, and from R to R. And what about R2? So let's see some of the examples in R2. So example 2. Say if you have f from R2 to R2, and when I say R2, it's just a Euclidean distance. So I should really say E2 to E2. And suppose f is like a translation, all of our favorite linear algebra functions, or rotation, or reflections, etc. They are all isometries, right? We all know this. So are all isometries. So they preserve all these functions, these type of functions, they preserve all distances. Let's say this, f of xy is equal to 2x to y. So question is whether you can give me any distance which is preserved. So what is PF in this case? So again, the definition of PF is you take all the distances that are preserved under F.
Only 0, no?
Yeah, so it will be just empty. Right?
Yeah.
It's empty,
Yeah, because they are positive.
Yeah. I'm taking only R positive. Yeah, but yeah. So it is empty, right? So so you don't actually these kind of suggest, and you can play like around these functions from R2 to R2. They either preserve everything or they preserve nothing, right? So there are other functions you can play with, like say projections. If you take projections, then they preserve nothing. So for example, projection on the first coordinate, you can easily see this. Like, so suppose you take 2 points with distance, say maybe 1 here, A and B, but then you project it on the x-axis, then you have the same image. So the distance between f of A and f of B is equal to, in fact, 0, whereas distance between A and B is 1. So no distance like will be preserved here, and one like you can actually even take any R will work. So, okay. So no distance is preserved. Again, PF in this case is empty. Okay, so I'm going to move here. This is the, in fact, like we cannot find it because there's a theorem which says that either it preserves one distance, or it preserves like at least one distance, or it preserves no distance. Like if it preserves one distance, then it preserves all distances. So either PF is empty or F is an isometry. Okay. So that actually is our motivating theorem here. From Beckman and Quarles in 1953. And the reason actually we were interested in this kind of question was because the case n equals 2, where we saw the examples, that reappeared actually in Brazilian Math Olympiad in 1997. And then at some conference, it was this problem as a puzzle. It was shared by Dmitro Yereshkin at Dartmouth College. And then we were doing it actually as a puzzle. And then we found out that there is a theorem which says in much more general, like n bigger than or equal to 2. And which I just demonstrated that n is bigger than or equal to 2 is necessary because we saw a function where PF is non-empty, but still F is not an isometry. Okay, I have to say that here. This function here also, hold on. So clearly F is not an isometry, or F is not even continuous. So yeah. Okay. So this is necessary in the hypothesis. Okay. So now a question is that what are the other spaces, other metric spaces that has preserve one, preserve all property? Okay. So that's the question. So we are going to define this. So we say that a metric space XT has the preserve one, preserve all property if for each f from x to x, either the preserved distances that set is empty or f is an isometry. So the Beckman-Quarles result implies that the Rn or En, when n is bigger than or equal to 2, has this property. So when we do some geometric properties in Euclidean space, and then we want to see something in general, the next interesting space is spheres. So what about unit spheres? Okay, so unit sphere, that I mean all these unit vectors. And the distance here is the angle between these vectors. So namely arc cosine of the dot product. So if you have that sphere, and here is your origin, then, and suppose your x is right here and y is right here. So x, say x, and here is your y. Then we say that the distance is just the angle here. Okay, so I'm going to give you an example and then we will just analyze this. So you have, suppose you take function f, and here is your north pole, the south pole, and I'm going to just map all the points. So f of x is equal to x if x is neither north pole nor the south pole, and then it interchange. So f of the north pole is mapped to the south pole and f of south pole is mapped to the north pole. Okay, that's how I'm defining my function. Let's see what is P, like at least like a couple of points in PF. So I claim that the pi is in PF. So pi is preserved. Okay, so if you have North Pole and South Pole, the distance between them is pi, and you are just switching them, so the distance is still pi. And other points, distance pi, antipodal points, they are not changed. So you have the same distances. Does that sound convincing? Any questions?
Yes, all good.
Can you, I'm sorry. Okay. Can you give me another number in other distance in PF? Can you think about that?
The trivial, the identity, I don't know.
Yeah. What about this?
It seems to me that it is preserved.
Yes, it is preserved.
You gave the hint, so it is easy to.
Yeah, think about that, because if you have North Pole and then you have something on the equator here, right? The great circle here in the middle, that will be pi over 2 distance. But then North Pole is going to South Pole, but still the distance between the 2 points is going to be preserved because the point on the equator is going to be the same as image. And then the other points, if it is one of the points is not North Pole or South Pole, then the other points are just mapped to the same points. So the images are not changing. Okay. So these are the 2 distances that are preserved. However, this is highly non-isometry because f is not even continuous, right? Isometry has to be continuous. If you see the definition, distance between the image points is equal to distance between the points. Isometry implies continuous. However, this function is not continuous. So f is . discontinuous. So, or you can just show that some other distances are not preserved. Okay. So clearly just n bigger than the dimension bigger than or equal to 2 is not actually just that hypothesis is not the only hypothesis which would work if we replace Rn by Sn. However, that actually brings another theorem that is known. So the theorem here, Everling proved in 1995 that if you have a sphere of like 2 or more dimension, then either smaller distance than pi over 2 is very crucial here, is the set with preserved distance and that interval is either empty or F preserves all distances. So F preserves sufficiently smaller distance than F preserves all distances. So this pi over 2 is really associated with this, and I'm going to talk about that. I will tell you that. So the idea here is that we might need to now assume that preserved distance is quote unquote sufficiently small. And then we have some evidence, and that made us actually make a conjecture, and this is our conjecture, that if you take X a complete Riemannian manifold, and I'm going to explain some of the terminologies, quickly review those, with dimension of X bigger than or equal to 2, and some notion of convexity radius, if it is bigger than 0, then for each function f, either you have this set empty, and remember this pi over 2 in a sphere is actually convexity radius of a sphere, which I will explain in a minute, or f is an isometry. And this is a conjecture, and I'm going to just give you at least one evidence, at least one supporting theorem that we were able to prove. Okay, so a quick terminology, because I was told that not everyone here is just I apologize in advance if it is too basic, but I just want to quickly recall. So we say that a smooth manifold is Riemannian manifold if for each point, you have inner product, so you have distance notion on the tangent space. And then if you have a curve in a Riemannian manifold, then we can define a length of a curve just exactly the same way, but here the distance is given by that inner product. So you just integrate the velocity, the length of the velocity vector at each point. And then you can view a Riemannian manifold as a metric space in the following way. So you can define the matrix, the function d, the distance function. So distance between A and B, you take all the curves joining A and B, this should be A and B, and then take their lengths and take the infimum of that. That is the distance between the points A and B. And we say that X is a complete Riemannian manifold if with respect to this distance, it is a complete metric space. And then there are some other equivalent conditions. And then there are a lot of theorems. So if you have a complete Riemannian manifold, then for every pair of points, there is a curve that joins point A to point B, with length of that curve is exactly the infimum of all the lengths of the curves that are joining A and B. So that means this curve is known as minimizing geodesic. And that is true if you start with a complete Riemannian manifold. And I need one more notion, which is a convexity radius in our conjecture, that we say that a subset B of a Riemannian manifold is strongly convex if for every pair of points in A and B in B, there exists a unique minimizing geodesic in X with endpoints A and B, and this minimizing geodesic stays inside B. And this is how we relate everything to define convexity radius. So the convexity radius is defined as follows. So you take all the metric S balls where S is in between 0 and R, and then you put, if they are all strongly convex, meaning they all satisfy these conditions like unique minimizing geodesic inside that stays inside that ball, and you take the supremum of all of these r's, like it turns out that, I mean, that's the notion that convexity radius. And it turns out that convexity, one can check that the convexity radius of Sn is pi over 2.
It is
So I want
always. I have a
to,
question. Is it
yeah.
always? It is always less than the injectivity radius. Yeah.
Yes, there is some relation. I think like the it is there is some connection to that. Yes. So the convexity radius is less than or equal to injectivity radius. Yes.
Yeah.
Mhm.
I am going to ask you. So, in this definition, I have a question. If these geodesics in this context, defined by this way, are equivalent to using the standard definition of geodesic, maybe using Riemannian geometry?
Yes. Yes.
Yes,
Yes.
yes. They are considering, because we are maybe all translating all the information in terms of the distance function.
Yes.
Okay, and are the same.
Yes. Yes. They are the same. Yes.
Okay.
Yeah. It's the same notion. Yes. Any other question?
Apparently not.
Okay. So then we have already seen that En, where n is bigger than or equal to 2, that's one our motivating theorem due to Beckman quarrels. Their convexity radius is actually infinity. So no hypothesis on convexity radius when they stated the theorem, and it went fine, like it's true. Then also hyperbolic spaces, the convexity radius is again infinity, and these Beckman-Quarles type result is true, proved by who's Mink in 1979. So these spaces are also, of course, n bigger than or equal to 2. These spaces satisfy the preserve one property. They have these. Then I just mentioned about Sn, the spheres by Everling. And then there are some other instances which I'm not like really like that familiar, but I know that the results exist, and they are about on something known as Hadamard manifolds. And then there are some hypotheses one has to put on a function. So bijections F on manifolds, they have preserve one, preserve all properties. And that was due to
Are there works for Finsler manifolds?
I'm not aware.
Okay.
Yeah. Okay. I need actually to prove, like to state our theorem, I need one more notion, which is we saw the set of all preserved distances. I'm going to say that these are strongly preserved distances. Preserved distances. And we are going to denote it by SPF. And again, the definition is almost the same, but we need actually stronger condition. So distance between A, B is equal to R if and only if, and this is the change here, one arrow. So now I'm ready to state our theorem. Here. That we could prove is, suppose you start with complete Riemannian manifold with convexity radius bigger than 0, dimension is bigger than or equal to 2. Suppose now there is a hypothesis on f, the function f2, if it is, let it be continuous or surjective. And then there is more hypothesis on what kind of numbers this has. So remember, this is not just PF. We couldn't get rid of S yet. So these are the strongly preserved distances. And suppose there exists two distances such that the ratio is not a rational number, then we could prove that F is an isometry. So there are some hypotheses, extra hypotheses that you are seeing it from our conjecture that we want to get rid of them. We have not been able to get rid of them. Still, like, it is kind of strongly suggestive that like our conjecture still holds. We are just not able to prove it, of course. But this is what we, one of the evidences like that, like we have proved. Okay. So to prove this theorem, just a strategy, just a very outlined strategy, is that you start with the distance, starting with a preserved distance. Preserved distance, you produce new and smaller preserved distances. And then use something known as immersion theorem, which says the following. Suppose X is a complete Riemannian manifold with our usual hypothesis that the dimension of X is bigger than or equal to 2. And F is a function self-map. And now if 0 is a limit point of this PF, then F is a smooth Riemannian immersion. Meaning that the length of the vector, and then when you apply the differential of that vector, it's the same for all tangent vectors or in the tangent bundle layer. So this is a strategy. Now, I'm just going to demonstrate in the last like maybe 10 minutes. I'm just going to demonstrate what kind of like how to produce new and smaller preserved distances. And the example that I'm going to do is going to be just the Beckman-Quarles theorem. This example. So suppose you assume that you have one distance preserved. How to get the smaller and newer distances preserved, and then how to prove that 0 all distances are preserved basically from there. So the first thing, I'm going to just assume now you have function f, you are in Euclidean 2 space, so easy. And now assume that one distance is preserved. Let's begin from there. Then you know that vertices of the equilateral triangle with unit side length are going to be mapped to vertices of congruent triangles because like the one distance is preserved, so easy. Now, I'm going to prove that square root of 3 is also a preserved distance, but I'm going to follow like one little step before that. So I'm going to say that if distance between 2 points is square root of 3, then either the image points is just the distance 0, or they are the distance is square root of 3. So I have here this rhombus, right? So you have here x, and then p, u, v, and y. And you see, notice that the distance between point x and point y is a square root of 3. So I have two equilateral triangles sitting on each other. Okay. I know that equilateral triangle, vertices of equilateral triangle, they go to are mapped to the vertices of a congruent equilateral triangle. So either we have this situation here, right? And then this also equilateral triangle, the triangle below also is mapped here, or it just collapses on the top of one another. So you have only two choices, okay? So that means either the distance between the image points f of x and f of y is either square root of 3 or it is equal to 0. Now let's show that distance square root of 3 is preserved. Okay, so this looks like a little complicated picture, but it is not. So I have 2 points, A and B, here, A and B, that are distance square root of 3 from each other. And what I drew here, I have a circle with center A, right, and radius square root of 3. That is my green circle. And I have a purple circle with center B and radius 1. That's my purple circle. And it's very important to note that they do intersect in point P. So choose a point P that is both on these circles or spheres in 2 dimensions. Yeah, I mean notice now that the distance between point P here and B is 1, and we are assuming that distance 1 is preserved. So we have this. And distance between point P and A is square root of 3 because point P is on both circles, radius 1 and radius square root of 3. Now, what we want to say is distance between f of A and f of B is square root of 3. If not, then they have to collapse the triangles there, right? So if f of A is equal to f of B, then we know that f of P and f of A, the distance is equal to 1 because we are just saying that f of B is equal to f of A. And that will be a contradiction because if 2 points are square root of 3 distance, then what we have shown previously that the image points are either distance 0 or they are square root 3 distance. And here we have a contradiction. We have actually distance square root of 3 points, but then you have distance 1, and that is a contradiction. And that's what gives us only one option, that the distance between f of A and f of B is square root of 3. So you might say that I just told you that we have to create new distances and smaller distances. What I did, I went from 1 to square root of 3, so which is a bigger distance. But we can use this square root of 3 preservation in order to show that 1/2 distance is also preserved. So I'm just kind of like going a little quicker here. So the conclusion of what we just proved is that the vertices of a rhombus with unit side length map to vertices of a congruent rhombus. That's what we showed. Okay, Using those rhombus, one can show that vertices of regular hexagon with unit side length are also mapped to vertices of a congruent hexagon, because you can place all these rhombus side by side and one can show that. And again, I'm going to step little ahead, showing that distance 2 is preserved using these hexagons. And then finally, we can actually come little smaller and say that distance 1/2 is preserved by using now isosceles triangles, because you can put the isosceles triangle in this way, where these are preserved, and then one can show that distance 1/2 is preserved. Again, you can go from isosceles triangle to another thing, and then you can show that 1/2 to the power 2 is preserved, and so on. So in general, one can show that 1/2 to the power L is preserved. And with using more, with doing some more work, one can show that in fact, all these rational numbers are preserved. And then you can use the limiting argument to conclude that if you have a distance which is say S, then that distance S is preserved by just approximating the distances and the known distances that are preserved before. And this is just using very simple fact that distance function is continuous. You can pull in the limits and use your knowledge that certain distances are preserved, and one can show that all distances are preserved. And when I said that in this picture, this point here is on intersection, that is important. We have used that in a general terms too. So there's some spheres, they do intersect in points, and the image of the intersection is the same as intersection of the image of the center points on the sphere. So we have used that in general to prove this, but then more work and more advanced techniques are needed to prove this theorem in general. Okay, I think I will stop here.
No, thank you. It's wonderful. we have some applauses, virtual applauses here.
Thank you so much. Yeah, thank you so much.
Yeah, we also have. We do not have fireworks, virtual fireworks, but we have these ones. Thank you, Meera. It was wonderful. Is there any questions from the audience? I don't see the. I am not on my.
Yes, I think Jonathan has
Jonathan.
Jonathan.
Mm-hmm.
Hi, good morning, everyone.
Hey.
And thanks for the beautiful talk. I have two quick questions. The first one is if the curvature has any relation with the preserving property, and the second one is I get lost about with respect to the Hadamard manifolds. Do they have the preserving property?
Yeah, so the Hadamard manifolds is something which I'm not familiar with. So, but yes, so these, if you have bijections, so if you have a bijection F from Hadamard manifold to itself, and if you have this SPF is not empty, then it preserves all distances. And that's what the theorem is, proven by Beretowski and Andrew. So it does have, Hadamard manifolds with some hypothesis on F has preserve one, preserve all property.
And what are non-examples?
Huh?
What are non-examples of Riemann manifolds that fails to have the property?
That's a good question. I'm I'm not sure actually, like other than just like very trivial things, right? Like R1, just a real real line. Um,
I have a question. Not that strong question, but are there more examples of general metric spaces which do not have this preservable property?
yeah, I think maybe that's what.
Literally lacks the
Yeah. And so definitely, I think I know that in our conjecture that we have shown. Just a second. Okay, there are definitely examples, and I'm not like able to recall that where some other number, not sufficiently smaller number is preserved, and still F is not an isometry. So like that doesn't have actually preserve one, preserve all property. Because if we need this condition here, so like the smaller distance needs to be preserved smaller than convexity radius, and it's not like I'm not recalling it, but I'm pretty sure that like there were some examples that we came across, and that's why we have put that restriction. Mm-hmm. So but like I don't know if we remove this, then I know that there are examples which I'm not recalling right now. But if we keep this, then I don't know. Like, and that's why we made the conjecture.
Yeah.
Yeah.
I have a related question with that.
Mm-hmm.
Uh, what was the definition of the convexity this convexity radius Cx?
What was the definition? Here.
Okay. Es que no, I can imagine what will be, I don't know, in a simple example.
Mm-hmm. So if you take actually say convexity radius of Sn would be pi over 2, because if you go beyond pi over 2, then there would be the minimizing geodesic, which wouldn't stay in that pi over 2, more than pi over 2 radius, because there has to be, first of all, unique, and then it has to be staying inside the ball. So one can see this, because all other spaces that we are considering, like En and then all of them, like the convexity radius is just infinity.
Okay, I have to think it more, but maybe some picture or some yeah, a picture.
Yeah.
It will be useful. But,
Yeah.
but thanks.
Mm-hmm.
More questions? Let me see. I'm not in my personal computer, but so that's why I cannot see if there are more
No.
questions.
No, there are not.
Not.
No.
No. I have a quick question. I don't know if this is really naive or even a stupid question, but what happens if you try to translate everything to not to a metric but to a pseudo metric? For instance, if you want to try to see the points where a pseudo metric is preserved or something like that. I am thinking about semi-Riemannian manifolds or something like that.
Yeah, I think it is not.
It is not even obvious what is going to be.
No, I don't know. Actually, this question was asked not like, yeah. So first of all, it is not a stupid question. Actually, this question was asked before by people, and I'm not sure actually what happens there. We have not thought about that.
Oh, I
Yeah.
see.
Yeah.
Thank you. If
Mhm.
there are no more questions, let's thank Meera again. We have again the
Thank you.
applauses.
Gracias, gracias. Thank you.
Yeah. De
Thank
nada.
you.
I know only those two words.
Muy bien.
Okay. See you
Thank
then.
you.
Yeah,
See
bye.
you. Thank you.
See
Yeah.
you.
Thank
Bye
you.
bye.
Thank you.